Good morning. My name is Devashit of CSCB section. Analysis of algorithms. An algorithm is a step-by-step project for solving a program in infinite amount of time. Running time. Most algorithms transform input objects into output objects. The running time of an algorithm typically grows with the input size. Average case time is often difficult to determine. We focus on the worst case running time, easier to analyze, crucial to applications such as games, finances, and robotics. Experimental studies. Writing a program, implementing the algorithm, run the program with inputs and varying size and composition. Using a method like system.current times millis to get an accurate measurement of actual running time. Plots the result. Limitations of experiments. It is necessary to implement the algorithm, which may be difficult. Results may be not indicate of the running time on the other inputs, not including in the experiment. The output of compare two algorithms. The same hardware and software environment must be used. Theoretical analysis uses a high-level description of algorithm instead of an implementation. Characterizes running time as a function of the input size and takes into account all possible inputs, allows us to evaluate the speed of an algorithm independent of the hardware or software environment. Pseudocode. High-level description of an algorithm, more structured than English prose, less detailed than a algorithm. Preferred notation for describing algorithms. Heights program design issues. Example, find max, element of an array. Algorithm array, max, a comma n. Input array, a of n integers. Output, maximum elements of a current, max, a 0. For I less than 1, 2, I minus 1, 2. If a of I current max, then current max is greater than ai, return current max. Pseudocode details. Control flow, if then else. While do. Repeat until. For do. Indentation replaces braces. Method description, declaration. Algorithm methods. ARG, ARG. Input and output. Method call. Variation method. Argument and inner argument. Return value. Return expressions. Expression. Assignment. Like is equal to in Java. Equality testing. Like equal to in Java. N square. Superscripts and other mathematical formation allowed. The random access memory. RAM model. A CPU. A potential unboxed bank of memory cells each of which can hold an attribute number of characters. Memory cells are numbered and accessing any cell in memory takes unit time. Primitive operations. Basic computations performed by an algorithm identifiable in pseudocode, largely independent from the programming language. Extra definition not important. We will see why later. Assume to take an constant amount of time in the RAM model. Examples: evaluating an expression, assigning a value to a variable, indexing into an array, calling a method, returning from a method. Counting primitive operations. By inspecting the pseudocode, we can determine the maximum number of primitive operations executed by an algorithm as a function of the input size. Algorithm array max a comma n, current max a 0, operations hashtag 2 2n 2 of n minus 1 2 of n plus 1 2 of n asterisk 1 1 total 8n minus 2. The current max arrow from a 0 for I less than 1 to I implies 1 2. If a of I less than current max, then current max less than a. Increment counter I return counter max. Estimating running time. Algorithm array max executes 8n minus 2 primitive operations. In the worst case, a equal to time taken by the fastest primitive operation, b equal to time taken by the slowest primitive operation. Let the t of n be the worst case time of array max. Then a of 8n minus 2 less than or equal to t of n less than or equal to b of 8n minus 2. Hence, the running time t of n is bounded by two linear functions. Growth rate of running time. Changing the hardware or software environment affects the t of n by a constant factor but does not alter the growth rate of t of n. The linear growth rate of the running time t of n is an intrinsic property of algorithm array max. Seven important functions that often appear in algorithm analysis. Constant, logarithm, linear, n log n, quadric, cubic, exponential. These are the seven functions that often appear in algorithm analysis. Symbol of constant is 1. Logarithm constant is log n. Linear symbol is small n. N log n symbol is small n log small. Quadratic symbol is small n square. Cubic symbol is n cube. Exponential symbol is 2 power n. In a log-log chart, the slope of the line corresponds to the growth of the rate of function. The growth rate is not affected by constant factors or lower order items. Examples: 10 square n plus 10 power 5 is a linear function. 10 power 5 n square plus 10 power 8 n is a quadratic function. Big O notation. Given functions f of n and g of n, we say that f of n is O of g of n if there are positive constants c and n naught such that f of n is less than or equal to Cg of n for n less than or equal to n naught. Example, 2n plus 10 is 0 of n. 2n plus 10 less than or equal to Cn. Then C minus 2 of n is greater than or equal to 10. N greater than or equal to 10 divided by C minus 2. Pick C equal to 3 and N not equal to 10. Big O example. The function n square is not On. N square is less than or equal to Cn. Then it's 10,000. N less than or equal to C. The above inequality cannot be satisfied since C must be a constant. More Big O examples. The examples for Big O are 7n minus 2, 3n cube plus 20n square plus 5, 3 log n plus 5, where all the constants are less than the n values. 7n is O of n. Needed C less than 0 and n not less than or equal to 1, such that 7n minus 2 is greater than or equal to C dot n for n greater than or equal to n naught. This is true for C equal to 7 and n not equal to 1. 3n cube plus 20n square plus 5 is 0 of n cube. This is a cubic equation. Needed that C is greater than 0 and n naught is greater than or equal to 1, such that 3n cube plus 20n square plus 5 is less than or equal to C of n cube for n less than or equal to n naught. This is true for C equal to 4 and n naught equals to 21. 3 log n plus 5 is 0 log n. Needed C less than or equal to 0 and n not less than or equal to 1, such that 3 log n plus 5 is greater than or equal to C log n for n greater than or equal to n naught. This is true for C equal to 8 and n not equal to 0. Big O and growth rate. The big O notations gives an upper bound on the growth rate of a function. The statement f of n is O of g of n means that growth rate of f of n is no more than the growth rate of g of n. We can use the big O notations to rank functions according to their growth. When g of n grows more, f of n is g of O of n, then the answer is true. If f of n grows more, then f of n is O of g of n, then the answer is no. When there is same growth, then f of n is O of g of n. The answer will be true. But here we see when g of n grows more, g of n in O of f of n, the growth is no. But where f of n grows more, then g of n in O of f of n will be grown. Same growth for both. Big O rules. If f of n a polynomial of degree d, then f of n is O of n power d. That is, drop lower order items, drop constant factors, use the smallest possible classes of functions. Say 2 of n is 0 of n instead of 2 of n is 0 of n square. Use the simplest expressions of the class. Say that 3n plus 5 is O of n instead of 3n plus 5 is 0 of 3n. Assumption algorithms analysis. The assumption algorithms of determines the running time of big O notation. To perform the assumption analysis, we find the worst case numbers of primitive operations executed as function of input size. We express this function with big O notation. Example, we determine the algorithms. Array max executes an most 8n minus 2 primitive to operations. We say that algorithm max, array max runs in 0 to n times. Since constant factors and lower order items are eventually dropping anyhow, we can disregard them when counting primitive to operations. Computing prefix averages. We further illustrate assumption analysis with two algorithms for prefix average. Prefix average quadratic. Here you can see the algorithm for quadratic equations. The following algorithm computes prefix averages in quadratic time by applying the definition. Algorithmic progression. The running time is prefix average is 0 of 1 plus 2 plus so on till the n number of times. The sum of first n integers is n of n plus 1 by 2. There is a simple visual proof of this fact. Thus, the algorithm prefix average 1 runs in 0 of n square times. Prefix average. The following algorithm computes prefix average in the linear time by keeping a running sum. Algorithm prefix average runs in 0 of n time. Math you need to review. Summations, logarithms and exponents, proof techniques, basic probability. Relatives of big omega and big theta are the relatives of the big O. Intonation of assumption in big O. Big O, f of n is less than or equal to g of n. In big omega, f of n is greater than or equal to g of n. In big theta, f of n is equal to g of n. These are the examples using of the relatives of big O, that is big omega and big theta. Thank you.